Thanks very much, Jejin, for the very kind introduction, and thanks to Andrew and all the organizers for putting together the workshop and for inviting me to participate. Um, as Jejin mentioned, I'm going to be describing a project that has to do with recovering sound from old postcards, and here's a kind of a roadmap. This talk is going to be, I think, a little bit different from some of the talks that you might expect to hear in a workshop like this. It starts with a kind of an unlikely collaboration with my colleague Tom Levine, who's in the German department here at Princeton. And it is going to visit a device that was invented more than a century ago called the phonopostal. That device was capable of inscribing sound onto a postcard called a Sonorine. And we have some of these Sonorine postcards, and our goal is to try to recover the sound from the cards and then eventually figure out what's being said, what's being spoken by the people who recorded on them. This is an ongoing project. We're in the midst of it, and I'm going to share with you today a few early results, but please don't go into this talk expecting that this is the full story. There's more to follow in coming months and years. It starts really with Thomas Edison, who invented a way to record sound in the late 19th century. And eventually, actually pretty quickly, he had a commercial product that could record audio onto a wax cylinder. And this is on the left, you'll see here an example of what one of these wax cylinders looked like. The cylinder would spin and the phonograph would record audio directly into the wax. And on the right here, I'm showing a quote from actually from Edison. He produced a newsletter, and this is from volume 1, issue number 1 from 1891. It says, Mr. Edison believes that the most important use of the phonograph in the future will be for epistolary purposes, phonograms being sent by mail instead of letters. And so he had this idea right from the very beginning that people would be able to record their voice and send it through the mail. Now, there was a problem with that idea, which is that the cylinders are made of wax and they're fragile and they're heavy, and it's just not appropriate to send them through the mail. So many of them were sent in the mail and were broken in the mail, and they're expensive to send. So it just really was not a great way to do this, but the idea was there right from the very beginning. And in fact, one of the primary use cases for these wax cylinders turned out to be dictation. So people would record their voice and then it could be used later for transcription, but typically not sent through the mail in the interim. Now, this might be more familiar to some people who are here in the workshop. There was a technology that was very popular in the 1940s and 50s where you could go to a recording booth, often at a place like Coney Island or the Empire State Building. And you could go into this booth and record your voice for something like 30 seconds or a minute and onto a record, and then send the record through the mail. This is more like a small vinyl record. And you know, some people may recognize here the face of Martin Sheen from the 1973 film Badlands. That was set in the 1950s, and it kind of shows what it was like to record in one of these recording booths. Now I can get to my colleague and collaborator Tom Levine. He's in the German department at Princeton University, but he's really a media theorist, and he's the co-director of our program in media and modernity. And as part of a research project for about a decade, Tom has been collecting these kinds of voice recordings, which he notes is the earliest form of voicemail. And in the course of doing this project, he ran across these postcards that turns out to be an earlier way of doing exactly the same thing that has really largely been forgotten. This is what looks like a normal postcard on the picture side, but on the back side of the card, this is the reverse side, with a little bit of an image enhancement, you can actually see that there's a sort of a spiral set of well, grooves that have been carved into a thin layer of plaster or something like plaster that's been coated on the card. So it's like a piece of cardboard or paper, like a normal postcard, but there's this very thin layer of plaster painted on one side, and inscribed into that plaster is an audio recording. And these were, it turns out they were quite popular, especially in France and in neighboring countries between 1905 and 1907. Since then, they've kind of fallen into obscurity. Nobody really seems to know about these things. One reason might be that there are just not so many of them that have remained. This is the device called the phonopostal that could actually record onto one of those cards. And you can see it's made out of what's called pot metal. It's a die-cast zinc. It looks a lot like a kid's wind-up toy from that era. And these were, they're not very sturdy devices. They were meant to be inexpensive so that people could have them in their home. And they were eventually or fairly quickly replaced by the gramophone. So they're quite rare today. We have actually 2 of those machines that we've been able to obtain for our project. And as far as we know, they're 2 of the only 4 that we're aware of in North America. Now, one of the design dimensions that I didn't describe yet, well, we already know that Edison invented a way to record onto a wax cylinder, so a cylinder shape. And later we saw recordings on discs that look like vinyl records. Now, cylinders used a kind of inscription called vertical inscription, where the sound was recorded onto the wax cylinder, where a needle would basically go up and down or in and out on the wax, and it produced these hills and dales on the recording. Later, when people were recording on vinyl records and all of those sort of disc technologies, they used what's called lateral inscription, which is that the needle would wiggle side to side, as shown here. So that ended up becoming the prevailing technology on discs. But these early Sonorines use vertical inscription, which has made recovering the sound a little bit more challenging than you might think, because you can't just look at where the grooves are and deduce the sound directly from that. You need to figure out how deep the grooves are. Here's a couple pages of instructions on how the Sonorines were recorded using a phonopostal. You'd basically shout into this paper cone, and then the device would inscribe the vibrations of your voice directly into the plaster surface of the card as the thing was spinning in a spiral. It also gives you a sense of the scale of the device. It's actually pretty small. It's hard to tell from the other photograph. One other observation is a completely amateur operation. It's not like people were going to recording studios using professional equipment. This is a thing you would have at home, and most people, they used it well or badly as you would expect amateurs to do. So it's not a professional recording. Here's the front and back of the card that I showed you, and I wanted to draw your attention to a couple holes that are punched along one edge of the card. Those holes were used to clamp the card into the device, the phonopostal, into a tray that sits on the top of the device, and it's that tray that would spin around underneath the needle. So you can see here, right here is one place where a hole would be punched, and here's another place where a hole would be punched. And that serves both to hold the card in place when the inscription is happening and when it's being played back, but also register the card. So when somebody would receive a card, they would know how to place it into the tray so as to get the proper playback. So you might think, okay, well, we have a couple of these devices, and Tom has a bunch of these cards. Maybe we should just start playing the card. Just put the cards on the device and play it back. Um, it seems like the logical thing to do, but uh, it I guess we this we think we would be afraid to do that because we don't know if playing it back would harm the recording. These are maybe 115 years old, and it's plaster. Who knows how sturdy it is at this point? Um, we don't really want to scrape a needle along the card and possibly damage. Each of these recordings is unique. There's just exactly one copy of it. It's not like a record album that you would get that was stamped out by the thousands or millions because it was popular. There's exactly one of these cards, and Tom has collected now more than 150 of them. I mentioned those holes punched in the card. It turns out to be quite advantageous for him. He can see when a card is listed on eBay or some other auction site, that it has a recording on it by the presence of those holes. And many of the collectors who have the cards don't even realize that's what they have. They think, oh, this card has been damaged because somebody stuck it into some kind of rack or tacked it up on the wall and punched holes in it. So now it's not quite perfect, and they're willing to sell it for cheap. So it's how he's been able to amass what we think is probably the largest collection of these things in the world. Okay, but so we don't want to play them back on the device, but we would like to know what's on the cards. It turns out I was describing for Tom a project that I'd worked on with a graduate student at Princeton and others back in 2009. The grad student is named Will Clarkson, and he was studying a way that we could uniquely identify blank sheets of paper by looking at the unique texture of the surface of the paper itself induced by the manufacturing process of pressing fibers together. So, for example, just to illustrate what I'm talking about, we're talking about the texture here. This is actually the surface of a piece of white paper. And here, just to give you a sense of scale, the word lorem is printed on using a conventional laser printer in 12-point font. So this gives you a sense of what is the scale of the texture that we're talking about. And the method that we used to capture this was to put the paper on a flatbed scanner and scan it 4 times at 4 different orientations, rotating it by approximately 90 degrees each time. And because the light comes in to the paper surface at an angle, the sensor looks straight down at the paper, so the light is coming in then from an angle. And if we rotate the paper each time, then that essentially rotates the light relative to that position. And so what we have is each position on the sheet of paper is lit from 4 different directions, north, south, east, and west. And then we can use standard photometric stereo to recover the shape of the surface of the paper. And when I described this project to Tom, he said, great, I have these postcards. I would like to get sound off of these postcards. And so we decided to work on this project together. And we recruited a couple undergrads who started working on it in the summer of 2017. And we also roped in my colleague Simon Ruzinkevich, who's been active on the project and provided a lot of advice, particularly on the engineering of on the capture side. And so here we see 2 bright Caltech undergrads, Angela and Harsh, and they have in front of them 4 computers connected to 4 scanners. You can see each scanner has an issue of the computer graphics journal sitting on top of it to kind of weigh down the lid of the scanner so that the card is really pressed flat against the glass. The reason that we had 4 of them going in parallel is because we wanted to scan these cards at high resolution, 1600 dpi, and we had to do it at each of 4 directions to get the 4 different, the 4 orientations to get the 4 different light directions. And actually, we scanned the front of the card too, so that was 5 scans, and each scan takes about 5 minutes. So it's because these are, I should have mentioned, these are cheap scanners. They're $75 scanners. So, so it takes quite a long time to scan a whole bunch of cards, but they worked their way through, and then started working on trying to recover the shape of the surface of the card. And so here are, you can see 4 different scans that have now been registered, and this is a close-up on one of them, and you can really see here is the sound inscribed onto the surface of the card. And it was that student, Angela Gao, who did a really great job in our first implementation of extracting a height field for every point on the surface of the card from those scans. And on the left, you can see that height field itself is really a mess. But if you take, oops, I went too far. If you take a look on the right here, here we've zoomed in on just part of the card, and you can really see the spiral grooves emerged, even though the scan itself is has led to a quite noisy height field. And here's a picture of Harsh working on trying to then follow those grooves, algorithmically follow those grooves in the height field. And you can see his code is sort of working its way around, but it doesn't make it all the way around. One of the challenges is you need a very good estimate of the center. And the way these devices are constructed, there's no hole punched in the center the way there would be on a normal, on a more modern record or on a CD. And just to illustrate the problem, you know, why we need that. So if the spiral were a perfect spiral, say, and this is the true center of that spiral, if we walked around the thing, say this red dot walked around the spiral, and we made a plot of how far away is that red dot from the blue dot as a function of the angle, we would expect this straight line, this blue line here. That is, it's the radius of the spiral is increasing linearly with the angle as it goes around. However, if you have an offset estimate of where the center is, so here the green dot is, say, a guess as to where the center might be, then if you look at the radius from the point of view of that center, as this red dot follows around the spiral, it'll make this wavy, the wavy green line. That is, it's sort of periodically longer and then shorter than the blue line. So we spent a lot of time trying to figure out a way to estimate where is the center. For example, here we looked on the card for places where there are strong gradients, figuring that those gradients would point us in the direction of the center. And indeed, it's pretty good, but not perfect. My colleague Simon figured out a very clever trick, which is that you can express this this green wavy curve as a sum of this blue, the blue line plus a sine function with unknown phase and amplitude, and then solve for the phase and amplitude if you are only able to find, say, part of the spiral, and then re-estimate the center from that learned phase and amplitude. And so another student, Ezra, implemented Simon's idea, and sure enough, that really locked in a good estimate of the center. So on the top, Ezra's first tracking of the groove, it was sort of wobbling up and down, but on the second track, it was just really locked in quite nicely. So with that, he was able to find and track the groove on one of these extracted height fields. And so here I'm showing the full Sonorine and then a close-up on the right, but I'm going to zoom in even more. Here I am zoomed in a little bit more and even more still and even more still. So here what the blue dots are places where we're actually taking samples of the height of the height field. That is that essentially is the encoding of the sound on the card. Where there's a red dot, it's because the tracking was lost and we had to interpolate from nearby blue dots, but the tracking is really quite good. The other thing I thought I would mention is that notice that it is not a perfect spiral. So here the gap between two rings, or I guess loops, is quite large compared to the next gap right here, which is small. This is somewhere in between and then larger. So you can see the device itself is not encoding a perfect spiral, and it's part of the challenge in following the thing. Another thing that's difficult about it is that what we're seeing here is the actual height, but it's the encoding of the sound, and you can see, so there's like a dark shadow right here and right here and right here and right here. Those are pits that are essentially carved into the surface of the card as the needle is vibrating up and down. And the spacing between here, from here to here to here, that spacing is one wavelength of the primary pitch that's being encoded on the card at that point. Okay. So here is one of the cards that we scanned. It's a postcard showing a famous painting from the time called The Meeting that hangs in the Musée d'Orsay in Paris. And next I'm going to play for you the sound that we recovered from the other side of the card. So here's the other side. Okay, here's another card, and I'll play the sound off that we were able to get off that one. I should say I don't speak French, although I do recognize croissant. So it's amazing to me, these cards went through the mail. This card, you can see, here's a postage cancellation. It's a piece of paper that went through the mail 115 years ago, and we're able to hear a voice that was encoded in that card. It's just amazing to me that we're getting anything out of it. Obviously, it's very noisy, and we're working to try to get a better representation of what's there. But I'm amazed. It's also got writing directly over the sound. One of the dealers who held this card wrote on here folklore, not realizing that he's writing directly onto the sound recording. So it's amazing that it's robust to that. We also have taken some of the cards to a place called the Northeast Document Conservation Center in Andover, Massachusetts, and scanned them on a very expensive and sophisticated laser-based system called Irene. This system is, I'm sure, a multi-million-dollar device. It was very expensive to scan the cards, maybe we spent something like $100 a piece, and it was also labor intensive. They had to then, having scanned it, they have to go and manually mark where is the sound on this complicated GUI. in order to extract it. And that said, the sound that they extracted from the cards is very much similar to the card. It's very similar to the sound that we were able to recover and that I played for you already. We've also been looking at a camera-based acquisition method where we have a fancy camera on a rostrum in our library, and we set up 4 different LED lights coming at different directions. Here I'm showing what the camera would see looking at a set of mirrored spheres. We use those for calibration. So here's the northeast direction, the southeast direction, turning on the southwest light, and then turning on the northwest light. And then having calibrated to those lights, we can, of course, recover sound using photometric stereo. And here's the northeast photograph for a Sonorine. Here's the southeast, southwest, and northwest. But I do want to point out, and I'm hopeful that we can get something out of this approach as well. But both the Irene and this very high-end camera-based approach would not allow what you see here, which is this is Tom scanning cards at the Bibliothèque Nationale in France. And well, if you're wondering why he's wearing a glove but no mask, it's because this photo was from last summer and the glove was archival, not related to the pandemic. In addition to his own collection, he's now been able to scan another 40 or 50 cards that we're yet waiting to try to recover sound from. And I'll play for you. I have a few more examples. I'll just play one of them because it's so fun to listen to. But I think I'll try to move things along and not do all 3. But here's just one of them. Also, I just wanted to make a quick plug for people who are interested in Sight and Sound, the Sight and Sound workshop. I think you'd be interested in a book by one of the I want to say foremost leaders in this field. His name is Patrick Feaster, and his book 1,000 Years of Educed Audio 980 to 1980. It's really an amazing book. It talks about how to extract sound out of a wide range of visual media, and it comes with a CD of examples that are illustrated in the text. So with that, I guess I'll conclude and say thanks to the organizers for inviting me, and thanks to all the folks who have contributed to this project. As I mentioned, it's an ongoing project. We're continuing to work on it this summer. And if anyone is interested, I'm welcoming questions or comments or suggestions as we go forward from here. So let's see. I'll stop sharing.
Thanks so much for the talk, Adam. That was really fun. Really interesting project. So it looks like there's a question in the chat, and I'll unmute you after you ask it. Andrew G asks, could you use the extracted audio to drive a reconstruction algorithm trained on old talking movies and modern recreations?
I know who the Andrew G is. It must be my friend Andrew Glassner. Thank you for a very creative idea. I always have such amazing ideas. I think that that it might be possible to train synthetic voices using recordings like these, also recordings in all kinds of media, to try to create, I guess, more authentic sounding representations of voices from the past. Your question also reminds me of something that I forgot to mention, which is these recordings that I played were just so noisy and terrible. You could barely hear the voice. Even if you speak French, it was hard to follow. One thing I would very much like to do is, once we can do a slightly better job of getting audio out, I also would like to train something to clean up the audio to get, I'm going to say, a more faithful representation of what that voice might have sounded like. So it's certainly related to your question. Thank you very much.
Great. And Justin asks, he says, very cool. Follow up, have you tried passing the output through an audio super resolution model to improve quality, e.g. ZU's work?
Thanks. That would be excellent. I would like to do that as part of the cleanup. We're actually extracting it at very low temporal resolution, because the way it's constructed does not do a great job of reproducing high frequencies. And it would be very nice, I think, if we could clean up the sound, to simultaneously also then do super resolution to reintroduce sort of plausible high frequencies. Of course, we would be hallucinating them, but we could do it based on,